lymphoid system. The lymphoid system protects against foreign invasions, such as macromolecules and microorganisms, and against virally altered cells. This system is composed of collections of non-encapsulated cells, known as the diffuse lymphoid system, and encapsulated collections of cells, lymph nodes, tonsils, thymus, and spleen. Innate immune system, the more primitive and evolutionarily older but faster responding innate, natural, immune system consists of complement, antimicrobial peptides, cytokines, macrophages, neutrophils, natural killer, NK, cells, and toll-like receptors. This system is nonspecific and does not establish an immunologic memory of the agent that elicited its attack. Table 12.1 lists acronyms used in this chapter. Adaptive immune system. The adaptive, acquired, immune system is specific and composed of T and B lymphocytes, T and B cells, and antigen-presenting cells, APCs, although they also use the components of the innate immune system to perform their task of protecting the body. These cells not only release cytokines to communicate with each other, but also contact one another, and by recognizing particular membrane-bound mold to combat foreign substances known as antigens. By definition, all antigens can interact with an antibody whether or not they can induce an immune response. An immunogen is a foreign substance that has the ability to initiate an immune response. The cells of the adaptive immune system release cytokines, recruiting cells of the innate immune system to assist in the response against the invading antigens. The adaptive immune system is typified by the following four characteristics: specificity, diversity, memory, and ability to distinguish between self and non-self. There are two types of immune reactions mounted by the adaptive immune system. Humoral immune response uses immunoglobulins, antibodies, manufactured by differentiated B cells, known as plasma cells. Antibodies bind to and either inactivate the antigens or mark them for destruction by macrophages. In cell-mediated immune response, a specific category of T cells, CTLs, is induced to contact the foreign or virally altered cell and drive it into apoptosis. The cells of the adaptive immune system develop in the bone marrow where B cells mature and develop into immunocompetent cells. T cells have to leave the bone marrow and enter the thymic cortex, however, to develop into immunocompetent cells. Immunocompetent B and T cells leave their primary lymphoid organs, bone marrow and thymus, to enter diffuse lymphoid tissue, lymph nodes, and the spleen, collectively known as secondary lymphoid organs. Here they search out and contact antigens. Clonal selection and expansion, to be able to recognize and eliminate all the possibly antigens and pathogens that one may contact in a lifetime. During embryogenesis about 10 lymphocytes are established. Each lymphocyte has the property of recognizing a particular foreign antigen. First contact with a particular antigen elicits a slow, weak adaptive immune system response, the primary immune response, because the B and T cells have never met this antigen before and are considered to be naive, virgin, cells. After contact, naive cells proliferate and form effector cells, plasma cells for humoral response, and CTLs, T helper TP cells Th1, Th2, T17, and CD regulatory T cells Treg cells for cell-mediated immune response, that respond to and eliminate the antigen, and memory cells that resemble NALV cells. Effector cells live for a long time, years, respond faster and more vigorously to a new challenge by the same antigen, secondary immune response, anamnestic response, and greatly increase the size of their clone, clonal expansion. Immunoglobulins, antibodies, a special family of glycoproteins, known as antibodies, immunoglobulins, is manufactured in enormous numbers by plasma cells and in small quantities by B cells, that place them on their cell membranes as SIGs, B cell receptors. A representative antibody, IgG, resembles the letter Y and is composed of 4 polypeptide chains, Fig 12.1. 2 long, identical heavy chains, secured to each other by disulfide bonds, form the stem and arms of the Y, where the arm and stem are held to each other by a hinge region. 2 short, identical light chains participate in the formation of the arms of the Y, each held to its heavy chain by disulfide bonds. Enzymatic cleavage of an antibody by papain occurs at the hinge region and forms an Fc fragment, the stem, whose amino acid sequence is constant, and two Fab fragments, antigen binding, each composed of a light chain and part of a heavy chain, whose distal portions are specific in their ability to bind only one particular epitope, the antigenic determinant region of an antigen. There are 5 different classes of immunoglobulins depending on various characteristic differences, Table 12.3. Cells of adaptive and native immune system. The adaptive and innate immune systems rely on the following cells: B cells, T cells, macrophages and their subtype APCs, and NK cells. B lymphocytes. B cells develop and become immunocompetent in the bone marrow. These cells manufacture IgM and IgD antibodies and insert their Fc end into their plasmalemma, SIGs, so that the Fab end projects into the external milieu. The Fc portion is affixed to the cell membrane by 2 transmembrane proteins, IgE and IgN, that, when the SIG contacts an epitope, transduce that information intracellularly, starting a sequence of steps whose consequences: activation of the B cell, whose responsibility is the humoral mediated immune system. Activated B cells proliferate to form plasma cells and B memory cells. Memory cells are responsible for donal expansion. Plasma cells manufacture IgM and then switch to a different isotype, Table 12.4. Certain polysaccharides, such as peptidoglycans of bacterial membranes, are thymic-independent antigens because they can initiate a humoral immune response without T-cell intermediaries. Only IgM antibodies are produced, however, and B memory cells are not formed. T lymphocytes, T cells develop in the bone marrow but have to enter the cortex of the thymus to express the necessary plasmalemma-bound molecules to become immunocompetent, see later in the section on the thymus. In contrast to B lymphocytes, T cells possess TCRs rather than SIGs. TCRs resemble antibodies in that their constant region is embedded in the plasmalemma, and their variable region, projecting into the intercellular space, binds to epitopes. Do not recognize epitopes unless APCs proffer it to them. About 200 different CD molecules have been identified. The TCR complex, consisting of TCR, CD3, and either CD4 or CD8, recognizes and binds to epitopes presented by APCs. Are able to act only in their immediate vicinity. Ignore non-protein antigens. Recognize epitopes only if they are associated with one of the 2 classes of MHC molecules of APCs. These molecules are genetically determined and are unique to each individual, characterizing the self. MHC class I are on the cell membranes of nucleated cells. MHC class II, and MHC class I, are on the cell membranes of APCs. T cells can become activated only if they recognize not only the epitope but also the MHC molecule. If the T cell does not recognize the MHC molecule, it cannot mount an immune response, therefore, T cells are said to be MHC restricted. T lymphocytes are classified into 3 broad categories: native T cells, memory T cells, effector T cells. Naive T cells are immunologically competent and have CD45RA molecules on their plasmalemma, but have not as yet been challenged immunologically. When they are challenged, they proliferate to form memory and effector T lymphocytes. Memory T cells possess CD45R0 molecules on their plasmalemma and are of 2 types: central memory T cells, TCMs, whose cell membrane sports CR7 molecules, and effector memory T cells, CR7 degree cells, TEMs, which do not have CR7 molecules on their surface. These cells establish the immunologic memory of the immune system. TCMs reside in the paracortex of lymph nodes where they bind to APCs, inducing the APCs to release IL-12. This cytokine causes TCMs to proliferate and form TEMs. The newly formed TEMs travel to the site of inflammation, differentiate into effector T cells, and respond to the antigenic challenge. IgM is the first antibody to be formed by B cells until T cells instruct them to switch to IgG synthesis. Individuals who have defective CD40 ligands are unable to switch isotypes and have excess blood levels of IgM, a condition known as hyper-IgM syndrome, resulting in humoral immunodeficiency-induced chronic infections. All nucleated cells possess MHC-I molecules, and these have to be recognized by CTLs to mount an immune response. Many tumor cells and virally altered cells stem the synthesis of MHC-I molecules to avoid being recognized and destroyed by CTLs. NK cells are able to destroy these cells, however, because they do not need to recognize MHC-I molecules. Effector T cells, effector memory T cells give rise to effector T cells, three different groups of immunocompetent cells that have the ability to mount an immune response. The three categories are Th cells, CTLs, and T killer cells, and Treg cells. All TP cells display CD4 molecules on their plasmalemma and have the ability to work with cells that belong to the innate and the adaptive immune systems. T cells also function in activating CTLs to kill foreign and virally altered cells and in activating B cells to differentiate into plasma cells to form antibodies. There are four subcategories of TP cells, a fifth one was placed into the Treg cell category, and they all secrete various cytokines. Table 12.6 Th0 cells, precursors of the other three classes of T cells, are able to release many cytokines. Th1 cells direct responses against pathogens that invade the cytosol. Initiate cell-mediated immune responses. Secrete IL-2, which induces mitosis in CD4 and CD8 T cells and CTL cytotoxicity. Secrete IFNY, which induces macrophages to destroy phagocytosed microorganisms and activates NK cells. Macrophages secrete IL-12, which causes formation of more Th1 cells and restrains production of TP2 cells. Secrete tumor necrosis factor E, which promotes acute inflammation by neutrophils. T2 cells function in prompting humoral responses against parasites and infection of the mucosa and secrete IL-4, which encourages B cells to switch to IgE production for allergic responses and, with IL-10 impedes the development of IH cells. IL-5 which prompts eosinophil formation. IL-6, which encourages formation of T and B cells to battle asthma and systemic lupus erythematosus. IL-9 which augments mast cell responses and TP2 cell proliferation. IL-13, which encourages B cell formation and retards formation of Th1 cells. TP17 cells secrete IL-17 and boost neutrophil response by facilitating their recruitment. They also develop from naive T cells if IL-6 and transforming growth factor are present. CTLs, in contrast to TP cells, have CD8 molecules on their plasmalemma. The TCRs of CTLs binds to epitopes on the plasma membranes of foreign, virally altered tumor cells. Additionally, CTLs insert perforins into the target cell plasmalemma, inducing creation of pores in the membrane. Secrete granzymes that enter the target cell cytosol through the newly formed pores, driving the cell into apoptosis. Possess CD95L, death ligand, on their plasmalemma and bind to and activate CD95, death receptor, on the target cell membrane, inducing the cascade of apoptotic death in the target cell. Treg cells also have CD4 molecules on their plasmalemma and function in suppressing the immune response. The two categories of Treg cells, which may function together to curtail autoimmune responses, are natural Treg cells, which stem an immune response in a non-antigen specific fashion by binding to APCs. Inducible Treg cells, previously known as Th3 cells, which secrete IL-10 and TGF- to prevent the formation of Th cells. In contrast to the other I cells, natural T killer cells are able to respond against lipid antigens that APCs with CD1 molecules on their cell surface present to them. Natural T killer cells are similar to NK cells in that they can be activated without intermediate steps, although only after they spent time in the thymic cortex where they become immunocompetent. These cells release IL-4, IL-10, and IFNY. Occasionally, the immune system develops a dysfunction, as in Graves' disease, in which the thyroid follicular cell's receptors for thyroid-stimulating hormone are no longer recognized as part of the self. Instead, these receptors become viewed as if they were antigens. Conditions where the self is viewed as if it were foreign are known as autoimmune diseases. Antibodies bind to the TSH receptors, causing the follicular cells to secrete an overabundance of thyroid hormone. Patients with Graves' disease present with an enlarged thyroid gland and exophthalmos, protruding eyeballs. Major histocompatibility complex molecules, MHCs, located on the surface of APCs, including virally attacked and virally altered cells, function in holding short peptides cleaved from antigens, known as epitopes, that are presented to T cells. MHC molecules of every individual differ from MHC molecules of other individuals. T cells can recognize the self. There are two types of MHC molecules. MHCI presents epitopes, 8 to 12 amino acids long, cleaved from proteins made by the cell. Endogenous protein, all nucleated cells, including APCs, manufacture MHCI molecules. MHC2 presents epitopes, 13 to 25 amino acids long, cleaved from phagocytosed proteins, exogenous proteins. Only APCs manufacture MHC2 molecules. Loading major histocompatibility complex I molecules, proteasomes cleave endogenous proteins into epitopes 8 to 12 amino acids in length. The epitopes, transferred into the rough endoplasmic reticulum by transporter proteins, TAP1 and TAP2, are bound to MHCI, and the complex is transferred to the Golgi apparatus for packaging and transport. The MHCI epitope complex is transported to the plasma membrane of the cell to be presented to CTLs, which determine whether or not the cell has to be destroyed. If the cell is producing viral protein, it is driven into apoptosis. If the cell is producing self-proteins, the cell is allowed to live. Loading major histocompatibility complex II molecules, exogenous proteins phagocytosed by macrophages and APCs are cleaved into increasingly smaller fragments in early and late endosomes, 13 to 25 amino acids long. Simultaneously, these cells synthesize MHC2 molecules on their rough endoplasmic reticulum, in whose lumen the MHC2 molecule temporarily binds class II associated invariant protein, CLIP. MHC2 CLIP complex enters the Golgi apparatus to be packaged and delivered to MHC vesicles, MHC2 enriched compartment, that also receives epitopes from late endosomes. Within the MHC vesicle, CLIP is exchanged for the epitope, and the MHC2 epitope complex is delivered to the cell membrane for insertion. APCs and macrophages present the MHC2 epitope complex to T cells, which determine whether to mount an immune response. Antigen-presenting cells. There are two types of APCs, members of the mononuclear phagocyte system, such as macrophages and dendritic cells, thymic epithelial reticular cells. B cells and APCs phagocytose and process antigens, load the epitopes on MHC2 molecules, place the complex on their plasma membrane, and present the complex to T cells. APCs release cytokines such as IL-1, IL-6, IL-12, and TNFN, which affect the immune response, and a host of other signaling molecules that function outside the immune system. Interaction among lymphoid cells. To mount an immune response, lymphoid cells interact with one another and examine each other's surface molecules. If the molecules of the presenter cell are not recognized, the lymphocyte to which they are presented is driven into apoptosis. If the molecules are recognized, the lymphoid that recognizes them becomes activated, that is, it proliferates and differentiates. For activation to occur, the epitope must be recognized. A costimulatory signal, either released or membrane-bound, must be recognized. T2 cell-mediated humoral immune response. For all thymus-dependent antigens, B cells internalize and disassemble their antigen Sig complex, load the MHC2, and place the MHC2 epitope complex on its plasmalemma to present it to a Th2 cell, Fig.12.2. Step 1. Th2 cell recognizes the epitope with its TCR and the MHC2 with its CD4 molecule. Step 2. Th2 cell CD40 receptor and CD28 molecule have to bind to the B cell CD40 molecule and CD80 molecule, resulting in the formation of B memory cells and plasma cells. Acquired immunodeficiency syndrome, AIDS, is caused by human immunodeficiency virus, HIV, which has the ability to bind to the CD4 molecules of T cells. After binding to the CD4 molecules, the virus introduces its core into the T cell, debilitating it. As the virus increases in number and infects additional T cells, the number of T cells diminishes, and the patient is unable to mount an immune response and succumbs to opportunistic infections. 2 cell-mediated killing of virally transformed cells. The ability of a CTL to kill a virally transformed cell depends on 2 conditions. It must receive signaling molecules from an activated Th1 cell. It must be bound to the same APC that is in the process of activating the Th1 cell, Fig 12.3. Activation of the Th cell occurs when the following 2 steps are achieved. Step 1. Th1 cell TCR and CD4 molecules must be able to bind to the epitope MHC2 complex of the APC, inducing the APC to place a B7 molecule on its plasmalemma. Step 2. Th1 cell CD28 molecule has to bind to the APC's B7 molecule, and the Th1 cell releases IL-2, IFNY, and TNF. Activation of the CTL occurs when the following 2 steps are achieved. Step 1. CTL CD8 molecule and TCR must recognize the APC's epitope MHC2 complex, and the CTL CD28 molecule must bind to the APC's B7 molecule. Step 2. 2 cell releases IL-2, which must bind to the IL-2 receptor of the CTL. The activated CTL proliferates because of the influence of IFNY. The activated CTLs bind, via TCR and CD8, to the epitope MHCI complex of the virally transformed cells and kill the transformed cells by inserting perforins into the transformed cell's plasmalemma, which cause the formation of large pores through which the components of the cytosol leak out of the cell, inserting perforins into the transformed cell's plasmalemma and releasing granzymes into the cytosol, driving the cell to apoptosis. Alternatively, the CTL's Fos ligand, CD95L molecule, death ligand, can bind with the transformed cell's Fos protein, CD95, death receptor, which drives the transformed cells to apoptosis. 2 cells assist macrophages in killing phagocytosed bacteria. Macrophages have to be activated by Th1 cells before they can destroy bacteria that they phagocytosed. This process requires that first the Th cell become activated. The activated T cell then instructs the macrophage to destroy the bacteria in its phagosomes, Fig 12.4. The activation of the Th1 cell requires 2 steps. Step 1. Th1 cell CD4 molecule and TCR have to recognize the epitope MHC2 complex of the macrophage. Step 2. Th cell activates itself by expressing IL-2 receptors and releasing IL-2, which binds to the newly expressed receptors and induces mitotic activity of the Th1 cells. The newly formed, activated Th cells bind to the macrophages with bacteria in their phagosomes. Step 1. The cell CD4 molecule and TCR have to recognize the epitope MHC2 complex of the macrophage, and the Th cell releases IFNY. Step 2. Macrophage is activated by IFNY and releases TNFN, which also binds to the macrophage. These 2 signaling molecules initiate the destruction of the phagocytosed bacteria by the formation of oxygen radicals. Lymphoid organs. Lymphoid organs are of 2 types: primary, central, lymphoid organs, fetal liver, postnatal bone marrow, and thymus, where lymphocytes become immunocompetent. Secondary, peripheral, lymphoid organs, lymph nodes, spleen, postnatal bone marrow, and mucosa-associated lymphoid tissue MALT, where immunocompetent cells can interact with other cells and with antigens to initiate an immune response against pathogens and antigens. Thymus, the thymus, a small endodermally derived organ located in the superior mediastinum, is divided into two lobes by its connective tissue capsule and functions in educating T cells to become immunocompetent. Although around the time of puberty the thymus begins to involute, degenerate, and becomes infiltrated by adipocytes, it is still functional in adults. Each lobe of the thymus is subdivided into incomplete lobules so that each lobule has its individual cortex, but shares the medulla with other lobules, Fig 12.5. The thymic cortex is occupied by numerous lymphocytes whose large nuclei and scant cytoplasm impart a dark, basophilic image in histologic sections. Immunoincompetent T cell precursors from the bone marrow enter the cortex of the thymus to proliferate and become immunocompetent T cells. To do this, they must contact various epithelial reticular cells of the cortex and develop some and eliminate other surface markers. T cell precursors from the bone marrow enter the corticomedullary junction of the thymus and migrate into the outer cortex, where they are known as thymocytes. Notch1 receptors on the thymocyte plasmalemma receive signaling molecules from the cortical epithelial reticular cells, causing them to become committed to the T cell lineage. Thymocytes begin to express some T cell markers CD2, but not CD3 TCR complex and not CD4 or CD8. Therefore, they are known as double-negative thymocytes. As the double-negative thymocytes move deeper into the cortex, nearer the medulla, they express, and then suppress, other proteins on their surface. These double-negative thymocytes express pre-T cell receptors, pre-TCRs, that cause the cells to proliferate. These newly formed thymocytes express CD4 and CD8 molecules and become known as double-positive thymocytes. The double-positive thymocytes rearrange their genes coding for the variable region of their TCR and express a low level of the CD3 TCR complex on their surface. The double-positive thymocytes that express low levels of CD3 TCR on their surface are tested by cortical epithelial reticular cells to see if they can recognize self-MHC self-epitope complexes. Most double-positive thymocytes, about 90%, do not recognize these complexes and are driven into apoptosis, and cortical macrophages phagocytose the dead cells. Some double-positive thymocytes, 10%, recognize these complexes and are allowed to mature, express higher levels of TCRs, and stop expressing both CD4 and CD8 molecules. When the T cells express either CD4 or CD8, they are known as single-positive thymocytes, and they leave the cortex to enter the thymic medulla. Single-positive thymocytes contact medullary epithelial reticular cells and dendritic cells that challenge them to see if the thymocytes recognize self-epitopes that were not presented to them in the cortex. Single-positive thymocytes that would mount an attack against the self are driven into apoptosis in the medulla, and the dead cells are eliminated by medullary macrophages, clonal deletion. Single-positive thymocytes that would not initiate an immune response against the self are allowed to leave the thymus to populate secondary lymphoid organs as NALV T cells. Epithelial reticular cells. There are 6 types of epithelial reticular cells, 3 in the cortex and 3 in the medulla. Type I cells isolate the cortex from the connective tissue capsule and trabeculae and form a sheath around blood vessels of the cortex. Type II cells are located in the midcortex and surround islands of thymocytes. They present self-antigens, MHCI molecules, and MHC2 molecules to thymocytes. Type III cells are located at the corticomedullary junction. They present self-antigens, MHCI molecules, and MHC2 molecules to thymocytes. Type IV cells are located in the medulla at the corticomedullary junction. They assist type III cells in isolating the cortex from the medulla. Type V cells form the architectural framework of the medulla. Type VI cells form thymic, hasals, corpus cles, release thymic stromal lymphopoietin that promotes clonal deletion, and assist in driving single-positive T cells into apoptosis. Some individuals who are born without a thymus, a condition known as DiGeorge syndrome, are unable to generate T cells and are incapable of mounting a cell-mediated immune response. Because T cells are required in the initiation of most humor-ally-mediated immune responses, these patients are mostly immunoincompetent. As long as patients with DiGeorge syndrome are protected from infection, they can survive. However, most die of infections, or because many of these patients are also born without parathyroid glands, they die of calcium tetany, severe hypocalcemia. The blood supply of the thymus first gains entry into the medulla and forms a capillary bed at the junction of the cortex and the medulla. Branches of these capillaries enter the cortex and immediately become surrounded by a sheath of type I epithelial reticular cells that are held to one another by fasciae occludents. These epithelial reticular cells form the blood-thymus barrier in the thymic cortex, which ensures that macromolecules carried in the bloodstream cannot enter the cortex and interfere with the immunologic development of T cells. The endothelial cells of the cortical capillaries and the type I epithelial reticular cells possess their own basal lamina, which adds support to the barrier. The space between the epithelial sheath and the endothelium is patrolled by macrophages that destroy macromolecules that manage to escape from the capillaries. The cortex of the thymus drains into the venous network of the medulla. Lymph nodes. Lymph nodes are usually small, bean-shaped structures, and 3 cm in diameter, with a convex surface and a concave surface, hilum, invested by a connective tissue capsule, Fig 12.6, that is usually embedded in adipose tissue. Deep to the capsule, the parenchyma is subdivided into an outer cortex, housing B cells that form primary and secondary lymphoid nodules. A middle paracortex housing IP cells. Deeper medulla, whose predominant cells are lymphocytes, plasma cells, and macrophages. The capsule on the convex aspect sends trabeculae into the cortex, subdividing it into incomplete compartments. As the trabeculae continue into the paracortex and the medulla, they become more tortuous and less definite, see Fig 12.6. Lymph nodes house T cells, B cells, dendritic cells, macrophages, and ATCs, and function in clearing lymph and initiating immunologic reactions against foreign antigens. Lymph enters the lymph node via afferent lymph vessels that pierce the convex surface and whose valves prevent the lymph from flowing out of the node. The lymph percolates through the node and exits, via efferent lymph vessels, which also have valves to prevent the lymph from re-entering the node at the hilum. Arteries enter and veins leave the lymph node at the hilum. These vessels use trabeculae to penetrate the parenchyma of the node. In the paracortex, the veins form high endothelial venules, HEVs. The incomplete compartments of the cortex of a lymph node are bounded superiorly by the connective tissue capsule and laterally by trabeculae derived from the capsule, see Fig 12.6. As the afferent lymph vessels pierce the capsule, they deliver their lymph into the subcapsular sinus, from which the lymph travels into paratrabecular sinuses that follow the trabeculae and deliver their lymph into the very tortuous medullary sinuses that are drained by efferent lymph vessels. These lymphatic sinuses are lined by simple squamous endothelial cells, and their lumina are spanned by an interdigitating complex of stellate reticular cells that not only slow the flow of lymph but also are used as scaffoldings by macrophages that phagocytose antigenic particulate matter. The cortical compartments display dark, spherical secondary or primary lymphoid nodules. Secondary nodules, see Fig 12.6, are formed as a reaction to an antigenic stimulation, and they actively produce B cells, centroblasts, that have not as yet expressed SIGs. Proliferation of these cells occurs initially in the dark zone and later in the light zone of the central, clear area, the germinal center. The centroblasts displace the resting B cells, pushing them away to form the dense mantle, corona, that fashions a cap over the germinal center toward the subcapsular sinus. Additional cells that are located in a secondary follicle are migrating dendritic cells, such as Langerhans cells of the skin, are bone marrow derived and are distributed throughout the body. When they detect foreign antigens, they migrate to the nearest lymph node to initiate an immune response. Follicular dendritic cells are not derived from bone marrow and reside in the lymph node. They present antigens to centrocytes, newly formed B cells that have expressed SLGS. Follicular dendritic cells force B cells with improper SIGs into apoptosis and permit the other B cells to differentiate into B memory cells and plasma cells, which enter the medulla and leave the lymph node. Reticular cells synthesize type 3 collagen, reticular fibers, which forms the architectural framework of lymph nodes. Macrophages destroy apoptotic cells. Primary nodules, see Fig 12.6, are resting nodules in that they do not have germinal centers or a mantle until B cells that were activated by T helper cells at the border of the cortex and paracortex migrate into the primary nodule to form a germinal center, transforming the primary into a secondary nodule. The paracortex, see Fig 12.6, is the T cell-rich region of the lymph node. Here HEVs permit the entry of B and T cells into the lymph node. B cells migrate to the cortex, and T cells remain in the paracortex. The medulla, see Fig 12.6, is composed of medullary sinusoids, trabeculae, and medullary cords, structures formed by reticular fibers, reticular cells, and macrophages, and B cells and plasma cells that were formed in secondary lymphoid follicles. In a healthy individual, lymph nodes are too soft to be able to be palpated. If the patient has a regional infection, however, the lymphocytes of the node draining that particular area proliferate, the node swells, becomes hard and painful, and may be palpated with ease. Each area of the body is drained by a series of lymph nodes that are connected to one another by lymph vessels. This formation of chains of lymph nodes is frequently responsible for the spread of infections or the metastasis of malignancy from one part of the body to another. As lymph percolates throughout the sinusoids of the lymph node, macrophages remove approximately 99% of foreign or undesirable particulate matter by phagocytosing it. APCs that contacted antigens make their way to the lymph node nearest to their location, present the MHC epitope complex to T helper cells, and initiate an immune response. When in the lymph node, these APCs are known as migrating dendritic cells. Antigens that enter the lymph node via the afferent lymph vessels are picked up by follicular dendritic cells, which present the epitope to resident lymphocytes. When the antigen is recognized, a B cell becomes activated at the interface of the paracortex and cortex, it migrates into a primary lymphoid nodule, and begins to undergo rapid mitosis, forming a germinal center, transforming the primary into a secondary lymphoid nodule. If the activated B cells express improper SLGS, they are driven into apoptosis by the follicular dendritic cells. If they present proper SLGS, they are permitted to continue to differentiate into B memory cells and plasma cells. Newly differentiated cells migrate into the medulla of the lymph node and form medullary cords. Approximately 90% of the plasma cells leave the lymph node via the efferent lymph vessels and migrate to the bone marrow, where they manufacture and release antibodies until they die. The remaining 10% of plasma cells stay in the medullary cord and manufacture antibodies until they also die. Most B memory cells also leave their lymph node of origin to seed other secondary lymphatic organs, where they set up small clones in case the same antigen invades the body again. A few B memory cells remain in their lymph node of origin and establish a small clone there. Spleen. The spleen has a dense, irregular, and collagenous connective tissue capsule that is covered by the peritoneum, a simple squamous epithelium. The largest lymphoid organ, the spleen has a convex surface and a concave area, the hilum, where the capsule sends connective tissue trabeculae, bearing blood vessels and nerve fibers into the substance of the spleen. Attached to the capsule and the trabeculae is a three-dimensional complex of type 3 collagen fibers with their associated reticular cells that form the physical framework of the spleen. In contrast to lymph nodes, the spleen is not divided into a cortex, paracortex, and medulla. Instead, it comprises white pulp, the marginal zone, and red pulp, sporting an abundance of tortuous sinusoids, that are intermingled, Fig 12.7, to serve the functions of the spleen, filtering blood and destroying senescent erythrocytes, forming T and B cells and mounting immune responses. Hematopoiesis in the fetus and, if the need arises, in adults. Vascular supply of the spleen, the large artery supplying the spleen, the splenic artery, forms several branches before it enters the substance of the spleen at its hilum, Figs 12.7 and 12.8. The vessels travel via trabeculae as trabecular arteries that provide numerous, ever smaller branches in correspondingly smaller trabeculae. When the arteries are 200 kilometers or smaller in diameter, they leave their respective trabeculae, and their tunica adventitia unravels and becomes mired in a sheath of T cells, known as the periarterial lymphatic sheath, PALS. The artery occupying the center of the PALS is referred to as the central artery. As the central artery becomes smaller in diameter, it loses its PALS, and it forms a series of small, straight arterioles that parallel each other as they enter the red pulp, known as the peninsular arteries, each of which has 3 sections: pulp arteriole, sheathed arteriole that possesses a coat of macrophages, Schweiger-Seidel sheath, terminal arterial capillary, which delivers blood directly into a sinusoid, closed circulation, or into the red pulp tissue in the vicinity of a sinusoid, open circulation, or, as believed by most investigators, in open and closed circulations. Veins of the pulp, see Fig 12.8, receive blood from the sinusoids and are drained by larger veins that accompany arteries of corresponding sizes in trabeculae that lead the larger veins to the hilum, where they form the large splenic vein. White pulp, marginal zone, and red pulp, the 3 components of the spleen are white pulp, marginal zone, and red pulp. White pulp is the sheath of T lymphocytes, the PALS, whose center is delineated by the central artery. Often a lymphoid nodule, composed of B cells, is formed within the PALS so that the T cells surround a spherical accumulation of B cells. If the nodule is responding to an immunologic challenge, a germinal center is also present. In the spleen, as in lymph nodes, T and B cells occupy prescribed regions, see Figs 12.7 and 12.8, marginal zone, a region approximately 1 wide is the interface between the white pulp and red pulp, see Fig 12.7. The cells of the marginal zone are interdigitating dendritic cells, APCs, macrophages, plasma cells, T cells, and B cells. Additionally, small sinusoids, marginal sinuses, abound in this region. Capillaries, derived from the central artery, enter the red pulp for a short distance, recur, and empty into the marginal sinuses. The red pulp, see Figs 12.7 and 12.8, is composed of vascular spaces, the sinusoids, surrounded by the stroma of the red pulp, the splenic cords, consisting of a network of reticular fibers that are invested by stellate reticular cells to prevent the collagen fibers from contacting the extravasated blood that percolates through its interstices and precipitating the coagulation cascade. The endothelial cells of the sinusoids are unusual in that they are fusiform cells whose longitudinal axes parallel the long axis of the sinusoids. The endothelium is quite leaky with wide spaces between adjacent cells through which blood cells can easily escape from the lumen into the splenic cords. Sparse, thread-like reticular fibers, coated with discontinuous basal lamina-like material, wrap around the endothelial lining of the sinusoids. The functions of the spleen. The functions of the spleen are intimately interconnected with the design of its vascular supply. The first region where blood entering the spleen contacts the splenic parenchyma is at the marginal sinusoids, where APCs search for antigens, and macrophages attack microorganisms traveling in the bloodstream. T and B cells leave the bloodstream through the walls of the marginal sinusoids and enter the PALS and the lymphoid nodules. At the marginal zone, interdigitating dendritic cells present their MHC epitope complex to T cells. B cells recognize thymus-independent antigens to initiate an immune response. They differentiate into plasma cells, most of which migrate to the bone marrow and make antibodies. Material that is not eliminated in the marginal zone enters the sinusoids of the red pulp to be eliminated there by macrophages. This material includes old platelets and senescent erythrocytes. Old erythrocytes are recognized because they lose sialic acid residues and have galactose moieties on their cell membranes. Mucosa-associated lymphoid tissue, the mucosae of the respiratory, digestive, and urinary tracts display non-encapsulated clusters of lymphoid nodules and lymphocyte infiltrations known as MALT. Examples are gut-associated lymphoid tissue, GALT, bronchus-associated lymphoid tissue, BALT, and tonsils. Lymphoid follicles located all along the mucosa of the alimentary canal, known as GALT, are composed of B cells with a peripheral association of T cells. The most prominent CALT is located in the mucosa of the ileum, known as Peyer's patches, Fig 12.9a. Aneroles supplying Peyer's patches are drained by veins, some of which are HEVs that permit the exit of lymphocytes and macrophages from their lumina, Fig 12.9bd. M cells, microfold cells, associated with Peyer's patches, trap antigens from the lumen of the gut and transfer these unprocessed antigens to APCs present in Peyer's patches. BALT is similar in morphology and function to GALT except that these follicles are located in the mucosa of the respiratory tract. Tonsils, a collection of partially encapsulated lymphoid nodules, palatine, pharyngeal, lingual, and numerous very small tonsils, are located at the entrance of the oral pharynx, protecting it from inhaled antigens. In the presence of an antigenic challenge, lymphocytes become activated and proliferate, enlarging the affected tonsil. The paired palatine tonsils, ensconced between the palatoglossal and palatopharyngeal folds, are covered by a stratified squamous epithelium and present about a dozen deep crypts that may house food and other debris and microorganisms and desquamated epithelial cells. The parenchyma of the palatine tonsils has numerous lymphoid nodules, some with germinal centers. The deep aspect of the palatine tonsils possesses a dense fibrous capsule. The unpaired pharyngeal tonsil, located in the nasal pharynx, is similar to the palatine tonsil except it has a respiratory epithelium covering it and shallow enfoldings, called pleats instead of crypts, and its capsule is thinner. When the pharyngeal tonsil is inflamed, it is known as the adenoid. The lingual tonsils, located on the dorsal aspect of the posterior one-third of the tongue, are covered by a stratified squamous epithelium that dips into the numerous crypts whose floor receives the posterior mucous minor salivary glands. The deep aspect of the lingual tonsils possesses a thin capsule. The parenchyma of the lingual tonsils is composed of lymphoid nodules, many of which display germinal centers.